Today, composite laminates have become a major part of structures for which weight matters. Long fiber laminates are made by stacking of layers with different fiber orientations. This creates complex structures that multiplies the number of interfaces and thus multiplies the number of possible damage mechanisms.
For example, a typical damage sequence in a 0-90-0 stacking sequence under tension would begin with the decohesion between the matrix and the fibers. The decohesion is quickly followed by cracking in the matrix, and these cracks will then propagate until reaching the interfaces between the different plies. The cracks will then induce micro and macro delamination between the plies. Eventually, the fibers in the 0 degree plies will start cracking and the laminate will fail. The complexity of the mechanics of composites is that damage sequence actually strongly depends on the nature of the loading conditions and on the structure of the composite material itself. The consequence of that is that there is a collective effort in the scientific community to develop generic models for the failure predictions of composite materials. This thesis is based on the belief that bottom-up approaches are the best strategy to develop such models. At the lower scales, these approaches rely on good models for each of the constituents of the composite material. So this research project actually focused on the characterization, understanding and modeling of a particular epoxy resin certified for aeronautics. And now I will show you a short survey of the combination of experimental and numerical studies that I conducted in order to reach these goals.
Epoxy resins are composed of a dense molecular network. At lower loads, intermolecular interactions prevent excessive and permanent deformation. Molecular dynamics have helped unveiling the nature of several molecular motions responsible for the accumulation of plastic deformations. However, there is still a huge gap between macroscopic constitutive models for glassy polymers, which consider the material as homogeneous, and the heterogeneous nature of the elementary deformation mechanisms. The lack of physics in these models prevents them from predicting several of the viscoplastic mechanical behaviors of typical glassy polymers. To bridge the gap between the two scales, I have considered that the molecular motions responsible for plasticity could be modeled explicitly in a finite element mesh, based on the shear transformation zone framework. This shear transformation framework was initially developed for metallic glasses, and for the first time it was considered for glassy polymers. This actually allows to directly account for the internal stresses which are generated around each plastic event. The ability of this model to properly predict the peculiar viscoplastic behaviors of glassy polymers clearly established for the first time the influence of the internal stresses on the response of glassy polymers. Of course, it is not possible to directly experimentally measure the mechanical response at the molecular scale. So we can now zoom out a bit and look at the first experimental test that was used to compare the behavior of the epoxy resin in the composite and in the bulk. Nano indentation consists in indenting with a pyramidal tip the surface of a specimen. It provides a direct measurement of its hardness and modulus over a certain displacement into the surface, up to a few micrometers. On this first set of pictures, you see the imprints of the indents in the composite specimen with different proximities to the fibers. The experimental results were combined with an extensive finite element post-treatment. The comparison of the results with different fiber proximities and the results obtained in pure epoxy enabled to visualize for the first time differences between the in situ and bulk properties. We can now switch to another experimental setup, the scanning electron microscope, more commonly called SEM. SEM is more frequently used to observe microstructure of unloaded specimens. In my thesis, I used a test device that allowed to load in compression composite specimen inside the SEM chamber. This setup enabled to directly observe the deformation process of the epoxy resin in the composite at the microscopic scale. With different level of magnification and the deposition of an alumina powder speckled pattern, it was possible to get a quantitative picture of the strain field at the scale of the fibers, with a sub-micron resolution. For example, for this particular specimen, where you can see a crack initiated in a small localization band between two fibers, a post-treatment using finite element simulation reproducing exactly the experimental conditions, and with well-validated models for the constituents, it was actually possible to show that different material regions corresponding to different material behaviors. It means that there is a clear difference between the in situ and the bulk mechanical properties of epoxies, and that this difference actually depends on the position of the resin within the composites, whether it is close or far away from the fiber. It is a significant shakeup for the composite community, as it is currently widely believed that the matrix behaves similarly in the bulk and in situ. This difference in behavior was exemplified by the fact that experimental transverse compression results obtained on thick unidirectional composites could not be reproduced in finite element simulations on representative volume elements. It was commonly accepted in the literature that such RVEs were representative of unidirectional composites. At the macro scale, what we call standard experimental tests were conducted on pure resin specimens. These tests easily allow to apply different loading conditions. I used a wide range of experimental tests, from pure compression to torsion or tension, and even tension under specimens. It is well known that epoxy networks tend to be very brittle under positive stress triaxialities, as in tension, and very ductile under compression. However, an in-depth analysis of the fractal surfaces resulting from the macroscopic test campaigns and the development of a simple fracture criterion enabled to prove that fracture always occurs because of the attainment of a critical stress at the tip of a pre-existing defect. The same critical stress must be reached in tension and in compression. So the large difference in ductility is explained by the increasing difficulty to reach this critical stress as the stress triaxiality decreases and that we tend to the compression case. Once again, the conclusions of this fracture analysis are critical for the predictions of damage initiation in composites. Indeed, it means that in the absence of pre-existing defects, it is the intrinsic microscopic critical stress that has to be accounted for rather than the usually used macroscopic strength.
The goal of this thesis was to study through the scales the mechanical behavior of a particle epoxy system. It provided the ingredients necessary for the good predictions of the matrix behavior in the composite. It is indeed critical for good predictions of damage initiation in laminates. Eventually, the thesis provided a deep understanding of the fundamental fracture process in epoxies. A single fracture mechanism and criterion was proposed and validated under a very wide range of stress triaxialities. It cannot be used for the prediction of damage initiation of an epoxy matrix in a composite. At the microscopic scale, in situ tests showed the large differences that exist between the mechanical response of epoxy between the fibers and in the bulk, and it showed the necessity to characterize the resin in the composite. More fundamentally, using the STZ model, this work showed that the origin of the viscoplastic behavior of epoxy resins lies in the very strong internal stress field which generated because of the very heterogeneous nature of the plastic deformation mechanisms.